Okay, this is a nice problem taken from the textbook by Incropera. It says a concentric tube heat exchanger for cooling lubricating oil is comprised of a thin walled inner tube of 30 mm dia. So this tube has a dia of 30 mm. This is carrying water and an outer tube of 50 mm diameter. So this outer tube is of diameter 50 mm and the outer tube is carrying the oil. So if you look at the hot and the cold fluid, the hot fluid flows in this direction and the cold fluid is flowing in the inner tube in the opposite direction. So it's a counterflow concentric tube heat exchanger. And the tube diameters are given. The exchanger operates in counterflow with an overall heat transfer coefficient capital U 70 watts per meter square Kelvin. And the tabulated average properties. So the average properties are tabulated here for you. You need not use the data book. When properties like these are given, you should avoid using the data book to take the properties. Now it's given that if the outlet temperature of the oil is 65, this is how oil is entering. So this is TO out. This is 65 degrees Celsius. Determine the total heat transfer and the outlet temperature of water. So you have to first find the heat transfer in the heat exchanger and you have to find the outlet temperature of water, TW out in their notations. Okay, so this is what you have to find. Secondly, you have to find the length required for the heat exchanger to operate. So how long should the heat exchanger be so that you achieve this heat transfer rate? So we shall start by first determining the heat transfer rate. Let's go back to our notation. We called the inlet temperature of the cold fluid as small t1 and the exit temperature of the cold fluid as small t2. So we are supposed to find t2, and because water is the cold fluid, we call it as MC. MC is 0.1 kg per second. And for the hot fluid, we'll do similarly. Mass flow rate of the hot fluid is 0.1 kg per second. And this is the entry temperature, so this will be capital T1 and this will be capital T2. So we'll write it in the data book notations so that it's easy for us. And not only that, we will also draw the temperature profiles in the heat exchanger. So let's be careful when we draw, because this diagram is given. Oil is flowing from right to left. So oil is coming in at a temperature of 100. So I will use the same direction of the heat exchanger that's given here. Capital T1 is 100 degrees Celsius and its temperature decreases as it flows through the heat exchanger. So this is oil and T2 is given to be 65 degrees Celsius. Now if you look at the temperature profile for the cold fluid, which is water, water is entering at 30 and it's leaving at some temperature. So we don't know the temperature, so I'll mark it somewhere here. So this is the temperature profile for water. Small t1 is given to be 30 and small t2 is something that we have to find. And the mass flow rate of water is given. Mass flow rate of the cold fluid is 0.1 kg per second. And the mass flow rate for the hot fluid is also 0.1 kg per second. Do I know the Cp values for oil and water? Yes. So here the Cp values are given. This is Cp for the cold fluid. So this is small cc. And this is the lowercase c for the hot fluid. So this is Ch. Oil is the hot fluid. And water is the cold fluid. That will be Cc. Okay, so we have all the data that we want to find the heat transfer rate. I will use the heat transfer rate formula as mH Ch delta Th, which is T1 minus T2. For the hot fluid, the heat that is given by the hot fluid is given by the mass flow rate into the specific heat into the temperature difference. Because I know all of them, I know the mass flow rate of the hot fluid, I know the specific heat from the table, and I know both the temperatures for oil it's given. So I can use this equation to compute the heat transfer rate. mH is 0.1, C for the hot fluid is 1900, and the temperature difference is 100 minus 65, and it turns out to 6650 watts. So this is the first thing that you have to find. What is the heat transfer rate in the heat exchanger? That's obtained by finding the heat given out by the hot fluid, because we know all the properties of the hot fluid. The second thing, so you determine the total heat transfer and the outlet temperature of water. Now we know this heat is the same amount of heat absorbed by the cold fluid. So I can write it as mc cc capital T2, small t2 minus small t1. For the cold fluid, the amount of heat absorbed will be the mass flow rate into the specific heat into its temperature difference. Now we know Q, we have to find what is the outlet temperature. We know the mass flow rates, the property is given, and the inlet temperature is given. Let me substitute 6650 equals 0.1 into, for water it's given as 4200 into T2 is something that I have to find, minus 30 degrees Celsius. So if you rearrange and calculate, you get T2 equals 45.83 degrees Celsius. Okay. So this is the exit temperature of water. So the first part of the problem is solved. In the first part of the problem, we had to find the heat transfer and the exit temperature of the cold fluid, which is water. We found the heat transfer using the mass flow rate, specific heat, and temperature difference of the hot fluid, and use that heat transfer to find the temperature difference for the cold fluid. And remember the assumption here, whatever is the heat given by the hot fluid is equal to the heat absorbed by the cold fluid. There is no heat loss from the heat exchanger. We are making that background assumption whenever we are solving heat exchanger problems. Now the second part of the problem, if you go to the statement, it says determine the length required for the heat exchanger. So let's try to now determine the length of the heat exchanger. We have to find the length of the heat exchanger. Now length is related to area, and area comes in the basic design equation that we have seen. Q equals U A delta T Lm. So if we are able to find out the area, from the area we'll be able to figure out the length of the heat exchanger. Now what all we have now? We found the heat transfer rate. U is given in the problem. The logarithmic mean temperature difference can be found for a counterflow configuration. So first let's find the LMTD for counterflow configuration. Going back to the figure, we see that at the inlet the temperature difference is 65 minus 30, which is 35 degrees Celsius, and at the exit the temperature difference is 100. We figured out this is 45.83. Now we know the temperatures. So 100 minus 45.83 is 54.17. So we can use these numbers to find the LMTD, or you can use the formula directly. The LMTD in counterflow is T1 minus T2 minus T2 minus T1 by logarithm of T1 minus T2 by T2 minus T1. If you do this, you get 35 minus 54.17 divided by logarithm of 35 by 54.17. Don't worry about the minus in the numerator, because log of a number which is less than 1 will also be a negative. You will get a cancellation. We get the LMTD as 43.89 degrees Celsius. So this is the LMTD for counterflow configuration. Now we can find the heat exchange area. The area is Q by U into LMTD. Q, we have found it as 6650 watt. The overall heat transfer coefficient in the problem is given as 70. U is 70, and LMTD we just found out it's 43.81. So we can find the area of the heat exchanger that is required in counterflow. If you calculate this, 6650 divided by 70, 43.89, 2.164 meters square, 1645 meters square. So we need a heat exchange area of 2.1645 meters square. Now if you look at this heat exchanger, where is heat transfer taking place? Because you are given two diameters, you have to be a little careful. Heat is exchanged between the hot fluid and the cold fluid. So heat is flowing from the hot fluid into the cold fluid. So if you look at the heat, it's flowing here, right, from the hot fluid to the cold fluid. So what is the area with which heat is crossing, or area through which heat is crossing? This area, which is the surface area of the inner tube. So the heat exchange area or the heat transfer area is the inner surface area or inner tube's surface area, which is pi d into L. And the diameter, the inner diameter is given to be 30 mm. So this will be pi into 0.03 into the length of the heat exchanger. Now, because you know this area is 2.1645, we calculated it here. You can rearrange and find the length of the heat exchanger. .97 meters. That's a huge length. Okay. So in single pass, if you want 22 meters, just imagine how long the heat exchanger has to be. So only if you have about 23 meters, 22.9 is approximately 23. Only if you have 23 meters of that heat exchanger for a 30 mm diameter, you can achieve this heat transfer rate and these temperatures. That's a huge length. Thank you.